afternoon, everyone. My name is Quang, and you can call me Rocky. I'm from Pakisis. And the title of my presentation today is Accurate Measurement of Nanomechanical Properties using the AFM for separation curve. So I will be talking about the effects of tip shape and friction on the mechanical property measurement. And this is the outline of my talk. I will first give a brief introduction about the nanomechanical properties measurement using AFM and related issues. And then I will move on to the experimental details. Also, in the third part of my presentations, I will be discussing about the measurement result obtained using 4 different tips. And finally, some concluding remarks will be made. So as you know, the quantitative understanding of mechanical properties at the nanoscale is very important for different applications. For example, at biomedical industry or the energy. For instance, the nanomechanical properties of the polymer binder plays an important role in maintaining the performance of the lithium-ion batteries. And also, the biological cell can sense and respond to the difference in the mechanical properties of the collagen fibers. So the AFM is widely used for measurement of mechanical properties at the nanoscale, especially the force spectroscopy or the force separation curve is conventionally used to get the information about the mechanical characteristic. So the force separation curve is a curve that represents the deformation or the separation of the sample with respect to the applied force by the AFM tip. And based on the force separation curve, we can apply contact mechanics theory to calculate the mechanical properties of your target specimen. And the conventional AFM tip can be modeled with very different geometries. For example, the spherical, flat-ended, parabolic, or the conical shapes. However, the selection of a proper geometry to model the tip is not straightforward. For example, when the deformation of the sample is much smaller than the tip apex radius, we can assume that it is a spherical contact. However, with the increasing deformation, we should use the parabolic model. And also, the conventional AFM tip often have the conical shape with the rounded apex. And therefore, to model this tip as a conical, the deformation should be large enough to minimize the effect of the tip apex. And also, the interfacial behavior, such as the sliding friction between the tip and the sample surface, can further cause the underestimation in extension and overestimation in the rejection of the signal from the photodetector. However, the effect of friction on the force separation curve is not explored yet, and also it is needed to systematically investigate the effects of tip shape on mechanical properties measurement. So in this work, the mechanical properties of 3 different polymers were measured using 4 different AFM probes with the spherical tip, flat-ended tip, and the conical tips with the rounded apex. So this is the force distance curve obtained on the sample using 4 probes. And you can see a slight hysteresis between the extension or the approach and rejection or the reject curve for all probes. However, the form of the hysteresis for the case of probe B is quite different compared to the probes A, probe C, and probe D. So the problem of probe B is due to the misalignment of the tip flat end and the sample, and this will be discussed later. So in general, the hysteresis for probes A, probe C, and probe D is due to the sliding friction between the tip and the sample surface. So the friction in the axial direction during approach and reject can cause a torque that opposes the normal bending moment of the cantilever. And as the result, the deflection signal from the photodetector is underestimated in the approach and overestimated in the result. Also, I should note that in AFM, the force distance curve is converted into the force separation curve by subtracting the cantilever deflection from the distance. And as the result, the hysteresis between approach and result is propagated due to this data conversion. So this slide shows the measurement result for the probe A. This probe has a spherical tip with a relatively large radius, around 7.6 micrometer. And you can see the polar force is significant for on sample. And also the separation or the deformation of the sample in this case is around few micrometer, few nanometer. So the ZKI contact models were used to analyze the result in this case. And you can see, due to the effect of friction, the Young modulus determined from the result curve are always larger than the approach curve. So by assuming that the effect of friction is the equal and opposite between the approach and the result data, the Young modulus of the samples in this case is calculated by taking the average value of the Young modulus determined from the approach and result curve and summarized in the histogram here. So I would like to move on the measurement result obtained using the probe B. This probe has a flat end tip. So for the case of a flat tip making contact with an elastic substrate, the relationship between the force and separation is expected to be linear. However, you can easily see that the slope of the force curve increases with increasing indentation. So this is due to the misalignment between the tip flat end and the sample surface. Due to the surface roughness of the sample or the misalignment of this probe with respect to the AFM coordinate system. And this kind of effect is typically observed in the microscale indentation measurement. So another issue is due to the misalignment, the local plastic deformation near the tip edge can readily occur, and therefore which cause further difficulty in the data interpretation based on the elastic contact model. So the overall result of the flat-ended tip measurement suggests that flat-ended tip is not recommended for the measurement of mechanical property, even at the nanoscale, and for relatively soft materials like the polymer. So here's the measurement result obtained using the probe C. This probe has a conical shape with the rounded apex. And this apex can be modeled as a hyperboloid of revolution. And the tip radius in this case is determined to be around 13 nanometer. So to consider the adhesion between the tip and the sample, the adhesive hyperbolic model was used to analyze the data. And you can clearly see the effect of friction on the measurement result, similar to the case of probe A. So I would like to move on the measurement result for the probe D. This probe also has a conical shape with the rounded apex. However, the tip shape in this case is relatively small. And also you can see the hyperbolic profile well describe the tip shape of probe D. But in this case, the uncertainty of the tip parameter determination is quite large because of the limitation of the SEM image. So in this case, I consider the upper and lower bound of the tip shape by the comparison between the profile and the SEM image. So the final tip radius is determined to be around 9 nanometer. And also for the comparison, I plotted the conical profile in this case. And you can see the distance around 25 nanometer between the actual tip and the conical profile. So this means that if you want to model this tip as a conical, you should have much larger deformation than 25 nanometer. However, the deformation of the sample in this case is smaller than 10 nanometer. So the hyperbolic adhesive model was used to get the Young modulus of the sample. So another issue of the property is the abnormal force separation curve often presented during the data collection. This is due to the pinning of the tip to the sample surface, which can be caused due to the local adhesion of the sample, the surface roughness, or the large local deformation. And these force curves were not included in the data analysis. So this slide summarizes the measurement results obtained using the props A, prop C, and prop D. So in general, we can say that the Young modulus value determined from three props agree within the experimental uncertainty, considering the large deviation of the Young modulus of the polymer materials. And also, because of the effect of friction, the Young modulus determined from the retract curve are always larger than the approach curve. In particular, for the case of prop A, we can see the largest difference between the approach and retract data, suggests that the effect of friction is more significant for the prop A. And the hysteresis due to friction can be dependent on the flexural stiffness of the AFM prop and the sample. So to further investigate this effect, the ratio of the Young modulus determined from the retract over the approach is plotted as a function of the K-con over Kn ratio. K-con here is defined as the contact stiffness at the maximum normal force. And this dependent on the A is the contact radius and the E is the effective elastic modulus. And also the Kn here is the flexural stiffness or the spring constant of the prop. So you can see the Young modulus ratio decrease with increasing stiffness ratios. So this suggests that the higher discrepancy or higher difference between approach and retract data can occur for softer materials. And also, based on this result, we can minimize the effect of friction by increasing the tip radius. However, with increasing tip radius, the adhesion between the tip and sample can readily increase and further cause the increase in the friction. And also, with the larger tip radius, we should use the larger flexural stiffness tip to apply the sufficient force for measurable indentation depth. Therefore, in summary, a prop with a minimal flexural stiffness is recommended as long as it can apply sufficient force. So in conclusion, the effect of friction should be minimized or avoided as much as possible for more accurate measurement of the mechanical properties from the force separation curve. And although the Young modulus determined from the spherical tip and the conical tip with the rounded apex agree with each other, a prop with a relatively large radius around 30 nanometer is recommended for few gigapascal Young moduli samples, considering the uncertainty can be due to the friction, tip characterization, or the force and separation measurement. So this is the end of my presentation. Thank you very much for your attention.